We are live. Well, in theory. Ooh, I'm going to get the pop-up chat. I can see myself on the internet. So,
Yeah,
are there
I can
any
hear you.
Belgians in the house who can help us understand what Trappist beer is? Because
How did this star get named after a beer?
what? What do you mean? Like, why isn't all telescope observatories named after beer? That's the bigger question.
Fraser's asking the real questions here.
Yeah. I mean, how?
I think Trappist stands for something.
It's a
Probably.
kind of beer. Apparently, there are
No,
like
Trappist is a monist, a kind of monk.
yeah, that's right. And the monks make the beer or something.
Yes, there's various monasteries, and they
Okay.
make beer.
Sam Lebrecht says he's from Belgium. Give us the details. Yeah, I am mirrored because this is the sort of collection picture. You'll see the there you go. Trappist beer is the best beer in the world. We have 6 of them in Belgium. There you go. They're made in monasteries. That is awesome.
Yep, and Trappist stands for Transiting Planets and Planetesimal Small Telescope.
No, it doesn't. It stands for a kind of beer made with love by monks in Belgium.
With telescopes looking for planets and planetesimals.
Right. Yeah, but no, I mean, like, why was it named after a beer? That's ridiculous, Morgan. I can't even believe you asked that question.
Paul, how much would Budweiser have to pay you to backronym a telescope to them?
Ooh. Would it be Bud or Budweiser?
Well, Bud would be pretty easy.
Actually, Bud Light. I bet we could do Bud Light.
Big ugly detector. Done.
Yeah. Bad.
Bud Light.
Ugly detector. You can't get away from ugly detector, can you?
Ultraviolet. Big ultraviolet detector.
There you go.
Um,
I'm going to say hi to a bunch of people. Hello to Adam Synergy, Ash Boone, Bill K, Brian Yoko, Brian Cordova, Colin Jones, Connor Lennon, Daniel McCool, Darth Chocolate. That's a cool name. David Dunn, Dusty Reichwin, Elid Avron, Frederick Ulfez, Galaxia, Giselle Sabarin, Guido Bibra, H. Roll, Helg Berkog, Ignati Romanov Cherengovsky, James Haney, John Suffield, Johnny Zed, Jorn Albert, Kenneth Lepre, Kjartan Savre, Larry Beckham, Linda Sadek, Logan F., Malcolm Bond, Max Decimus, MC Deuce, Michael Jobin, Mike Anderson, Morgan Renberg. Hey, wait a minute. He's here in the show. Nancy Graziano, Nelson Cruz, Paul from AstronomyNJ.com, Paul Gracie, Paul M. Sutter, also in the show, Peter Schultz, Renko Prozo, Raza Siddiqui, Rick Schwartz, Ronald McCoy, Sam Lambrecht, Shane Geary, Susan Hunter, Susan Murph, Tak Tang, The Blender Tree, Timothy Barnes, Tom C., Tomas Naiwadomski. Oh, you knew I was going to have problems with this, didn't you? I'll get better at it each week. Got to show up every week, and I'll just keep practicing. Tommy K., Tori Gadwa, William Hutchins, Zach Cody, and Zap Van Zap Van. Hey, everybody. Welcome to the pre-show to the Weekly Space Hangout. And thanks to all the kind words for crossing the 100,000 subscriber mark. We did it. Yay. We've got a video coming out on Trappist like today. It's like written and it's filmed and it's in editing right now, so we should have it out really quick. There's a dark matter beer in BC. Has Fraser tried it? I have tried it. We also have a Sputnik beer, which is really good, and we've got a UFO pale ale. Which is or no, it's a Indian. Yeah, it's an Indian pale ale, and it's like super, like hop crazy in the hop department.
The Planck collaboration commissioned a special wine.
Oh, really?
Our public data.
B-Som says, "What about me?" Well, you had to say hi before I started saying hello to everybody. So. Oh, cool. So Elad Avron's saying that Universe Sandbox 2 added the TRAPPIST system today, which is great. We actually used Sandbox. I should let Chad know so that he doesn't have to try and recreate it in Universe Sandbox. Okay, so Kimberly is not joining us today. too busy. Apparently something happened in her field this week. I don't know. So instead, we're going to bring the news and try the best that we can to explain it. We've got a planetary astronomer and an astrophysicist. There's got to be some, and an
some
amateur.
mild overlap.
Some
of
mild
extra
overlap here.
topics.
Yeah. There you go. And for Beer Talk, get Amy your title. She's the expert on good space-related beer. Good call. Anytime, Amy. Just show up. We're ready. Okay, well, let's do this thing. Let's change that. There's me. Here we go. See, it's not reversed now. It's normal. Hello, everyone, and welcome to the Weekly Space Hangout for Friday, February 24th, 2017. I'm Fraser Cain, publisher of Universe Today. This week, we're mostly going to talk about TRAPPIST-1, 7 Earth-sized worlds orbiting a red dwarf star. We're going to talk a little bit about a bold new plan to recategorize Pluto again, and a bit of an update on what's happening with SpaceX. We're mostly just going to show a really cool video. And then something else. What was it? Oh, yeah, Juno. And problems with its rocket and why it's going to have a little bit more of a boring orbit than normal. So, joining us this week, we've got whoever this person is. It's Paul Metzetter.
That's me. That's who I am.
Also joining us this week, we've got Morgan Renberg.
Hey, Fraser. Happy Friday.
There he is. Awesome. Okay, so I just want to remind everybody that this is a live interactive show, and it's just the three of us, no special guest. So we're gonna be spending.
Special.
Oh, we're all special. We're going to be spending a lot of time. We're going to talk about this crazy discovery this week. Put it in context for you. We're going to raise your hopes, bring back down again. It's going to be a party. So go ahead, post any questions, comments into the chat. You can either do it in the YouTube chat if you're watching this live, or if you're a member of the WSH crew, that's what this chat is right down here, you can join that as well. If you want to join the crew, which you really should, go to wshcrew.space and they will show you the ropes, let you get into the community. And really, this is the behind the scenes, the production team that works on this show. So we couldn't do this without them, and huge support for that community that surrounds us and helps us bring you the news. So if you want to go deeper, make sure you join this community. All right, let's get on with the story, and obviously the big one, something TRAPPIST-1, 7 planets. Paul Metzetter, go.
Yeah, no big deal. Just 7 Earth-sized planets, 3 of them in the habitable zone, orbiting a single star that's only 49 light years away. No biggie. Whatever. We can move on to the next story.
Okay. All right. So now we've known about TRAPPIST-1 for over a year now. And in fact, there was an announcement back in May 2016 with some of the planets. So what's the big story that was announced this week?
Yeah, so like you said, in May 2016, the TRAPPIST team, which stands for a Transiting Planet and Planetesimal Small Telescope, I feel like that name was chosen so that they could call their mission they discovered 3 planets orbiting this star, but then they did a follow-up observations with the Spitzer Space Telescope. And the Spitzer Space Telescope is an infrared telescope. And that's important because this star that's 40 light years away is in what's called an ultra-cool dwarf. It's smaller than our sun. It's redder than the sun. Most of its light output is actually down in the infrared range, not up here in the visible. So if you want to study this star in more detail, an infrared telescope is the instrument of choice. And they actually, Spitzer's, I don't want to say it's on its last legs, but it's been up there for a while. I remember working with Spitzer data something like 10 years ago. And they actually kind of reconfigured it. It wasn't originally a planet hunting telescope. It originally had totally different science goals and missions. But they were able to do some clever tricks with the telescope itself, some clever tricks in software and data analysis, so they can look at this star and look for transient events. And What do you know? Instead of 3 planets orbiting this star, there are at least 7. There might actually be more, but we've got 7 confirmed planets. And with the Spitzer data, we are able to get their size and their mass. And so we can tell that all the planets are about the size of the Earth, plus or minus a little bit. And based on their mass, 3 of the planets that are in the habitable zone have the right densities that match the densities of liquid water.
And the discovery, of course, is made with this red dwarf star and the planets going around that. So I think it's really important to put this in context. I mean, this star has 8% the mass of our own sun. This isn't another sun, and these aren't other Earths, even though they are in the habitable zone.
Well, obviously this star is nothing like our own sun. It's much redder, it's much dimmer. But roughly, if a planet is in the habitable zone, it receives about the same amount of sunlight that we do here on Earth. So the total amount of energy that these planets are getting from their host star is about the same amount of energy that the Earth gets from the sun. So in that sense, even though it's a totally different kind of star, in that sense, it is kind of Earth-like.
Well, okay, sure. So I mean, the main one, the one that we're most interested in, I think it's what, D in the planet.
Yeah, I think so.
It's getting an Earth's amount of illumination from a sun that's putting out vastly less energy, and so it's tucked in.
But it's closer.
It's tucked in really tight. Yeah.
Exactly. And so that means these planets are most likely tidally locked, unless of the planet always points towards the star.
You just hiccup for a second there, but yeah.
Tidally locked, the same face of these planets always faces the star. But since they're so close, there might actually be some extra dynamical interactions that might introduce some extra rotations. We don't know that for sure.
Oh, like they could actually have some kind of gravitational interaction with each other.
Some sort of
brings
resonant
back some kind of right. Okay, but in general, they are so close to their star that they are. They're
most
locked
likely.
like the moon. Okay, so what does locked mean to the chances of life on a planet?
Honestly, we don't know. If there wasn't an atmosphere and if there wasn't liquid water on these planets, then for sure, one side of the planet would be baking hot and the other side of the planet would be super frozen cold. Because one side would always be in shadow, permanent night, and the other would be in permanent day. But if there's atmospheres, if there's liquid water, then just like what happens in relations, there could be transport of heat energy from the day side back to the night side, through the oceans or through the atmosphere. And so maybe these planets are miserable hellholes, and maybe not.
Yeah. And then, of course, one of the other problems is that it's a red dwarf star, and they are known to be a little temperamental, especially when they're young. And this one's young.
So this one's young. Red dwarfs are much more temperamental than medium-sized stars like our own sun. We had the same discussion with the announcement of Proxima b, a planet around our nearest neighbor, Proxima Centauri. Proxima Centauri is the same class of star. In fact, most stars in the universe are this class of star. Most stars are small red dwarfs. So most planets in the universe by default are going to orbit stars like this. And so, if there's extra solar flares, if there's extra activity, if these planets don't have strong magnetic fields or don't have thick atmospheres, that's going to be a little bit of a radiological hazard for life on those planets.
Yeah, it's a bit of an understatement, right? That flare stars are red dwarf stars, and they can have flares that just dwarf anything that the sun can put out, and would just scour the planets of life. But the astronomers have said that it's actually not that bad. It's a pretty reasonable, pretty well settled star compared to some of the flare stars out there.
I think the excitement here isn't necessarily, is there possibly life in the TRAPPIST system? To me personally, that's not the most fascinating thing about this announcement. To me, the most fascinating thing is that, wow, Earth-like planets in the habitable zones around stars are ridiculously common. I mean, the star that's down the block, we don't just find one Earth-like planet, we find 3 of them all orbiting the same star. Just how common are Earth-like planets?
Morgan, I know you were hanging back here for a bit, but let's talk a bit about the distance. 39 light years, I believe.
Yeah, that's right.
Can we visit it anytime soon?
Unfortunately, we're not going to visit that anytime soon. We've talked on this show previously about this breakthrough starshot idea of sending a fleet of small spacecraft to the nearest star, which is about 10 times closer than the TRAPPIST system. And we've poked all sorts of holes into notions of quickly traveling between us and the Proxima Centauri system or the Alpha Centauri system. And this, while still close to us in a galactic sense, is very, very far away in some sort of human scale absolute sense.
Yeah, and so, I mean, you're a planetary astronomer as opposed to necessarily our resident exoplanet astronomer. How, if you could get up close, what kinds of questions would you be wanting to have answered about this system?
Yeah, it's interesting. It's from a planetary science perspective, it's sometimes difficult to really sort of get on the bandwagon with the notion of these as habitable worlds. Because if we look at our own solar system, by the sort of broad definition that we use to identify habitable worlds in other star systems, our solar system also has 3 habitable worlds. We have 3 Earth-like planets in the habitable zone, depending on what parameters you want to pick. That'd be Venus, Earth, and Mars. And we know from our studies of those worlds that they could hardly be more different. Mars is 100 degrees colder than the Earth. We know that Venus is hundreds of degrees warmer. Mars has a very thin atmosphere. Venus has a crushingly thick atmosphere. They're all relatively similar in comparison to, say, a gas planet or an ice giant or something like that. But for the question of can this world support life, small differences make big impacts. And that's not to say that one or more of these 7 planets might not be a good place for life, but with the sort of basic bulk measurements that we can make with our current telescopes, it's really difficult to pin down, yes, this meets even sort of the broadest definition for what life is.
Yeah, I mean, from what I've read, there's they've said that the atmosphere makes a big difference in this situation. So one of them could be habitable. Even the ones that seemed like they're outside of the habitable zone could be habitable. None of them could be habitable. Like, that atmospheric composition makes a big, big difference in this place.
It's critical. I mean, think of the Earth system again. The Earth is 1 astronomical unit away from the sun, and it's relatively temperate. We have liquid water on our surface. We have a complex water cycle. Obviously, we're covered in life. Venus is about 3/4 of 1 astronomical unit away from Earth. It's hundreds of degrees. It has the pressure equivalent to being under almost a kilometer of ocean. No liquid water, no complex liquid system on its surface, and as far as we know, no life. I mean, 1/4 of an astronomical unit is not that far on even a solar system's terms, and it's the difference between having a complex hydrologic system and basically a burning hellscape.
But getting back to your point about how complicated it is, this question of how do we measure habitability? If you had a planet at Venus's orbit, but maybe it was only half the size or 3/4, have to be low enough so it doesn't accumulate that thick of an atmosphere. Maybe there's no runaway greenhouse effect. Like Morgan rightly said, there's so many things that go into habitability, true habitability, that for now the best.
Yeah, and the James Webb Space Telescope
Oh,
We're losing Paul here.
yeah, we're losing Paul.
The James Webb Space Telescope is sort of poised to really help us start to answer some of these questions. Because one of the things that can help us figure out the temperature on a planet is the composition of its atmosphere, like Paul said. And we can make sort of basic guesses at that with our current technology. We can say, yes, there might be oxygen of some level in this atmosphere or not. But James Webb is going to be able to break down the components of an exoplanet atmosphere with a much higher level of precision. And we'll be able to say, okay, there's carbon dioxide or there's methane, and we can then know from our experiences in our solar system, well, what does that mean if you're getting this much heat from the star and you have a planet about this size and you have about this much carbon dioxide? What does that tell you about what the temperature must be like on the surface? And once we can start to break that down, we'll be able to say much more candidly, yes, this is a world that could be like Earth in a meaningful way.
All right, so we've got a couple of questions here. This one comes from Abdullah's Alamadi. How do they know that there is water on the planets? Morgan.
Do we know there's water on these planets? Maybe I'm out of the loop.
I don't think we do. I mean, I think that's the point, right? They're in the
habitable
zone.
So there's some things that we can sort of deduce. And so we know that rocky planets like the Earth or Mars or Venus are made of stuff of a certain density. And we know that gas planets like Jupiter, Saturn, Uranus, and Neptune are made of stuff of a much lower density. When you find something in between those two, you can often sort of infer that there must be a combination of less dense water and more dense rock. Another way we can sometimes do it is by looking at the atmosphere. Because the Earth's atmosphere, one of the primary greenhouse gases that we have is water vapor. That's the fluffy clouds that we see on a sunny day. And we can actually tell how that water vapor in the atmosphere affects light coming from that planet and get a sense of whether it's there or not. But we can't say it's liquid water or it's water vapor. We just say there's water there.
Paul, I was sort of going into this discovery. I mean, like every time I get an announcement from NASA, they're going to make some major announcement, I always find it's like actually a little underwhelming. I'm not as impressed as I think I'm going to be. And in many cases, I spend my time then, helping bring everyone's expectations back down. This one felt like it was worth it. How do you feel?
It was a good announcement. Yeah, it was a good announcement. And I think it's important to keep the perspective and what keeps scientists motivated, what keeps researchers motivated. Answering the question, are we alone, is going to be a very long haul to get to that answer. That is a deep, deep, difficult research question. So every step along the way, we ought to pause and we ought to celebrate and we ought to congratulate all the hard work of all the researchers and instrument operators and astronomers that made that next step. This is exactly what science is. It's iterative, step by step, year by year, even generation by generation to push towards an answer. Deal. We should show the public as we're taking this nice, slow, deliberate process to answering this deep question. And this was a major step, I think.
Morgan, we've got a bit of a conversation going on in the chat just about orbital resonances. Can you talk a bit just about how these worlds are going to be kind of connected to each other gravitationally and what impact that might have on sort of the worlds themselves? We talked a bit about that, but...
Absolutely. So this idea of resonance is very common in physics, and it's extremely common in orbital mechanics, the part of astronomy that basically studies how stuff moves under the influence of gravity. And the idea is that you have frequencies that basically line up. So the Earth goes around the sun in 1 year. Saturn goes around the sun in 20 years. If those were to be exactly multiples of each other, we might say they're in resonance. Now, of course, everything is an exact multiple of everything else for some number.
Right.
But what we care about
together, yeah.
Right. What we generally care about are small integer numbers. And so the planets in this system are in things like, we'd say it's a 3-to-2 resonance. And what that means is that one of the planets goes around the star exactly 3 times, for every exactly 2 orbits that the other one makes. And that means that every third orbit of that outer one, they line up. So they're very close to each other, and their gravity kind of self-reinforces. And so resonances are very stable things, because if you took one of those and you sort of pushed it a little bit away from that resonance, then when they came close to lining up, when they're supposed to be lining up exactly, gravity between them would sort of tug them back in the direction of the exact lineup point. And this can allow an orbit that would otherwise, say, become very circular to maintain a bit of oblateness, sort of be elongated. And we see this most prominently in the Jupiter system, where the 3 inner satellites of Jupiter, Io, Europa, and Ganymede, are on a 1 to 2 to 4 orbital resonance. And this is what drives the powerful volcanoes we see on Io and the liquid water ocean that we see underneath the surface of Europa.
Right, and you sort of led into then, I guess, what was going to be my next question is that, when you compare the size of this system, it is very similar in size to the Jupiter system. I mean, they're actually like these planets are orbiting this star as closely as Jupiter's moons are orbiting Jupiter. And we know that Io has tremendous tidal forces. It's pretty much volcanic all the time. Even Europa, further out, there's a lot going on. Are there going to be significant tidal forces going on with these planets orbiting their sun?
It certainly wouldn't be surprising if there were. Now, to have a tidal force like that, you have to have an orbit that's not perfectly circular. And so one of the things that it doesn't have to be much off of circular, but it has to be not perfectly circular. And so one of the things that we'll look to refine better is our understanding of the orbits of these planets. And this can provide a tremendous source of energy for one of these worlds. And that opens up the possibility that a world that might be somewhat outside of what we typically think of as the habitable zone, because maybe it's a little too cold now, so the water on the surface is frozen. If you could put in this tidal energy, you could generate a lot of heat, melt a liquid water ocean under the surface, and create a potential habitat for life somewhere where we might not expect it in sort of a classical habitable sense.
Yeah, just like that, the outer icy moons of our own solar system are outside the habitable zone, but look, there's liquid water all over the place.
Right. And under the surface, yeah. Paul, let's talk a bit about sort of following on observations. What comes next? I mean, this is like the beginning of this story, I think. Using Spitzer was great. James Webb is like a super Spitzer. So what does the future hold?
Yeah, so actually in the short term, Kepler has its eyes on it and will be monitoring the system for something like, I think, 70 days total of integrated observing time, which will help us pin down even tighter the masses and the orbital parameters. We might be able to learn, like Morgan said, if these planets are in resonance, which would cause some ellipticity in their orbits, which will give them some extra tidal heating. And then, the follow-up is the James Webb Space Telescope. Let's zoom in. We look at the sunlight or starlight from their host star, from the TRAPPIST-1 star, as a chemical composition is in there.
And I think one of the other things that's pretty important is that the initial observations, this TRAPPIST telescope, is based on the ground. It's in Lucia, Chile. It's a ground-based observatory, not a really tremendously large telescope and equipment that's used. And I think we've been talking about this in the past. We had a long conversation with Kimberly a few weeks ago that we're in a kind of a new place where we're able to make pretty amazing observations of exoplanets even now from the ground. Mm-hmm. So
there's all these that are using one telescope for detection, then another telescope to immediately follow up. We're using these for exoplanets. We're using these for supernova follow-ups. There's so much great science that isn't being based on these very super large, super expensive ground and space-based telescopes, but instead networks of smaller telescopes dotted around the globe.
Morgan, we've got a question here from Brian Yoku. How does the habitable zone calculation factor in atmosphere, magnetic fields, tidal lock of planets? It doesn't, right?
The sort of basic typical habitable zone that we often talk about factors in none of those things. If you're talking about sort of a particular system that you might have reason to suspect has an atmosphere of some kind or another, you can add that into the calculation and try to come up with something a little bit more specific. But when we're doing broad surveys of the galaxy looking for habitable planets, we know little to nothing about a planet's magnetic field or a star's magnetic field. We know often we don't know whether they're tidally locked. We often know little to nothing about their atmosphere. And so we just start with the sort of simplest calculation that we know. And that is how large is the star, how hot is the star, how large is the planet, and how close or far away is the planet from the star. Those are things that we can understand and measure pretty effectively. And those allow us to sort of make these broad generalizations about what it would mean to be habitable or not.
I mean, does that mean that maybe it's time for a whole new definition of a habitable zone as we get these follow-on observations? I mean,
if we start to get
atmospheric observations, right?
Yeah, if we start to get atmospheric observations for every exoplanet, then we might, it'd be wonderful. We might then think about redefining our definition. But sort of one of the key things about definitions, and I think we'll talk more about definitions later in this show, is that they have to be sort of workable. If you make a definition that we can't possibly know whether or not we're meeting it, then it's as good as not having a definition. And so we have to come up with definitions that work with the observations we have now, and then be willing to revise those definitions down the line once we understand more and have the capability to make more observations about things.
Yeah, and I think that's really the key, is that, you know, you offhanded mentioned, like, wouldn't it be cool if we, or when we can start to observe the atmospheres of all of these worlds, then we can start to get we've got more parameters that we can look at for extrasolar planets and their habitability and redefine the habitable zone. But really, until we do that, all we've got is the distance from the star, which is unfortunate. Which means that we really have to do that. We have to get that ability to observe those atmospheres, because it's like nothing is more important. The moment we can follow up on all of these planets with these atmospheric observations, then we start to kind of go life, not life, life, not life. I mean, that's next level, right?
Yeah, I'd like to put in a good word for life in the TRAPPIST system. I'm often the one here that kind of smacks down talk of whether these systems have life or not. But one of the sort of key things we always have to think about when we're talking about whether a system could potentially have life is how old is this system? Because life takes time to arise. And we don't know the exact age of the TRAPPIST system, but the early numbers that I'm seeing suggest that it's at least 500 million years old. And the good news is that there's circumstantial evidence here on Earth that life arose within the first 500 million years, perhaps as soon as within the first 400 million years. Now, we can't prove that. But we have lines of evidence, more than one, that suggests that by 500 million years into the history of the Earth, there were small unicellular life forms on Earth. The idea that there might be intelligent life on the TRAPPIST system is pretty far-fetched. It took billions of years of evolution to develop even sort of basic intelligence here on Earth. But the idea that TRAPPIST, one of those TRAPPIST planets, could harbor life of some sort is not far-fetched from this sort of time scale perspective.
Right. If we're going to look for life on Enceladus and Europa, it makes sense for us to look for life on these worlds as well. Yeah. Jorn in the chat just mentioned a better definition, the Earth Similarity Index, which I'm actually not aware of. I don't know if you've heard that term before.
One of the problems with, this is, and I've talked about this many times on this show, is how do we define and search for life? We can look for life that is like the life that we see here on Earth. And that's why we have the habitable zone definition based primarily around the need for liquid water. But that is a very small portion of all envisionable possible forms of life in the universe. And what we might have to come to terms with is the notion that there could be kinds of habitable worlds out there that we are not able to sort of envision of right now, and that we might be seeing worlds with life all over the solar system, and we just don't know yet how to look for it. Now, it doesn't make a lot of sense to sort of dwell on that fact because there's nothing we can do about it. Until we find life that looks different from us somewhere like in our own solar system, we can't just make up a billion definitions for life and then start looking for things that match that. But if you're wanting to sort of think about the grand history of our galaxy and the grand history of life in the universe, then I would say take heart from the idea that just because we look at a planet and says this wouldn't support Earth life doesn't mean it couldn't support life in some form at some time.
Right.
Yeah, I think that's a really good point. I mean, I'm sure there's a wide variety of life. The reason we focus on Earth-like planets around sun-like stars with habitable zones and liquid water is at least we know exactly what our kind of life looks like. And so we can look for the precursors. We know what the necessary conditions are. We know what the sufficient conditions are, and we can go hunting for that. So even though that narrows the possible horizon of possibly detecting life, we might miss something in our narrowly focused search. At least we know exactly what we're looking for. But yeah, keeping a broader.
Well, and the other thing, of course, is that we've got time, right? Or TRAPPIST-1 has time. It's only been around for 500 million years, but it is on the very low end of a red dwarf star. It's going to last for 4 to 5 trillion years. It's just going to keep putting out that same amount of energy. So can we talk a bit about these red dwarf stars and why they're different from the larger stars like our own sun?
Yeah, so the life cycle of a star is tied to its mass. And the reason for that is the bigger the mass of a star you have, the greater the gravitational pressure in the core, and so the faster the rate of fusion reactions that can happen. So big giant stars just chew through their available amount of hydrogen relatively quickly. And then medium-sized stars like our sun, steady rate but still pretty hot, and then they eventually run out of usable hydrogen in a few billion years. But these small systems or small stars, they're just on the edge of igniting a nuclear chain reaction in their core, just a low energy output, but also low fuel uses of the galaxy. They're not going to go super fast, but you can get a lot of mileage out of them.
Yeah, it's a terrible analogy, but I like to think of this sort of from the campfire perspective. If you've ever built a campfire and you just built a huge bonfire, you burn through all your wood in like an hour. But if you want to sit there and cook marshmallows, you can build a little fire and stoke that fire for all night, into the next day with the same amount of fuel.
And so there's more to it as well, right? Which is that in a star like our own sun, right, you've got these 3 zones. You've got the core where the fusion is actually happening. You've got the end of where the fusion happens, and you got the radiative zone where the only way that the photons can escape is doing this random walk from place to place. And then outside of that, you've got this convective zone, which is like a lava lamp, and all of the hydrogen fuel is kind of mixing, but the problem is that it's not making it down to the core.
Yeah, that's why I was careful to say usable hydrogen.
Yeah, the usable hydrogen.
There's these boundary layers in our sun that prevent most of the hydrogen in our sun is never going to be fused. But one of these smaller stars where they can convect all the way from the surface down to the core, you can bring in to participate.
And so if someone could take a big spoon and mix up the sun to get that outer hydrogen into the core through that radiative zone.
I saw that episode of Star Trek.
Yeah, exactly. Yeah, then that's a way that you could make the sun live longer. But as Morgan said, these red dwarf stars as well sip their hydrogen for a very long period of time. And so we know that life here on Earth got going, as Morgan said, within 500 million years. Like as quickly as it could, it happened. Run the clock forward for trillions of years. I like those odds. Okay, well, I think we've sort of exhausted this topic. There's a bunch of comments, conversations. I think we covered most of the ideas. One thing that I just did want to bring up, some people are asking about SETI. Should we listen to this world? SETI Institute already on it back in 2016 when these worlds were discovered. They turned their radio telescopes at TRAPPIST-1 and gave it a listen, and nothing. So far, there's no signals from aliens at TRAPPIST-1. All right, let's move on. Speaking of signals from... No, I can't do it. Morgan, let's talk about Pluto. Right there.
Yeah.
Does it get to be a planet now?
It does get to be a planet if you want to subscribe to the new definition that the new members of the New Horizon team proposed to the International Astronomical Union this past week. The problem is that so do 101 of its best friends. And so this is a story that's been developing now for more than a decade. You go back to 2006, and the IAU approves a new definition for what it means, in fact, the first ever definition for what it means to be a planet, because we started discovering all of these Kuiper Belt objects. And suddenly it seemed like there weren't 9 planets, there were dozens of planets. And this caused scientists to stop and think about, what does it mean to actually be a planet? And for the first time, we wrote down a definition of what that is. And I think it would be an understatement to say that definition would be controversial.
Yeah.
And it's made up, the old definition was basically made up of 3 parts. Number 1, you had to be in orbit about the sun. So this canceled out things like planetary moons. Number 2,
also exoplanets.
Yes, and it also didn't cover anything with planets around other stars. Number 2, you had to be large enough that your gravity pulled you into basically a sphere. And number 3, you had to have cleared the area or the neighborhood of your orbit. And that's the one that ultimately defeated Pluto, because Pluto is in orbit about the sun, and Pluto is large enough to be roughly spherical based on its own gravity. But it has this moon Charon that is so large that it was deemed to have not cleared its orbit. And obviously, that was distressing to a lot of people, but it was also just for people who didn't really care about Pluto's particular status. This definition was pretty problematic, because what does it mean to have cleared your orbit? We think that Jupiter might have more than 1 million asteroids larger than a kilometer that orbit in the same orbit as it. So has Jupiter cleared its orbit? And, we look out into stars around, or planets around other stars, and even if we modify the definition to be in orbit about a star, not in orbit about the sun, how do we tell that an exoplanet has cleared its orbit or not? We were just talking about how little information we have about these worlds. There's no way for us to tell in most cases whether or not it's cleared its orbit. So in response to this, a new definition has been proposed, and I'll just go ahead and read the definition, and then we'll break down what it means. The definition says, a planet is a substellar mass body that has never undergone nuclear fusion and that has sufficient self-gravitation to assume a spheroidal shape adequately described by a triaxial ellipsoid regardless of its orbital parameters. And so let's just break that down by section. A planet is a substellar mass body. That means that it has a mass too small to be capable of fusing hydrogen and be a star. That has never undergone nuclear fusion. This eliminates things like white dwarfs and neutron stars, the remnants of old stars that are now smaller than the mass of a star, perhaps, but did in one point in their past become part of a star. Then it has to have sufficient self-gravitation to assume a spheroidal shape adequately described by a triaxial ellipsoid. This is actually basically a fancier way of wording one of the parts of the old definition, which is you have to be big enough to be basically a sphere. And then finally, regardless of its orbital parameters. And this is sort of the poke at the old definition that put some limits on what a planet could be simply based on its path around the sun. And if you look at this definition and you apply it to the solar system we see today, you find that there's 110 planets in our solar system, including the 8 we have today, including Pluto, including Charon, including Kuiper Belt objects like Eris, including asteroids like Ceres, but also including things like the moons of Earth and all the gas giants. So our moon is a planet, Ganymede is a planet, Europa is a planet, Enceladus is a planet, et cetera, et cetera. And so this new definition, in my mind, corrects some of the problems we had with the old definition while introducing some new problems of its own.
All right, so let's see where we all fall. Now, first, I want to remind everybody watching this that we've got Dr. Alan Stern, known Pluto apologist, who is going to be joining us. He, of course, the primary investigator of the New Horizons mission. Huge fan of Pluto. He is going to be really standing up for Pluto, and we'll definitely get in with
This is his definition.
This is his definition, exactly. So,
going contrary to the irrelevant astronomical union, as he calls it.
Exactly. And so I just want to make sure that people understand that Alan Stern is going to be here next week. We really like Alan. We want him to still come next week. So it may be that we're going to have a biased conversation here, and we may sell out our journalistic integrity to make sure that Alan Stern does join us. Personally, I don't care. Like, I just don't care. I don't care whether Pluto is a planet or not a planet. Like, Pluto's awesome. And we just saw it up close, and we just saw Charon up close, and they are fantastic. And the sort of the hang-up about whether it is a planet or is not a planet, I don't really, it doesn't change how amazing the fact is that these worlds are out there in the outer solar system and the tremendous views. I mean, they have mountains of ice and oceans of like solid or something, methane and ethane and other kinds of volatiles. They have atmospheres, incredibly weird worlds, and they're just worth enjoying. We're never going back to 9 planets. Once Eris was discovered, and it's about the same size as Pluto, is it going to be 10? Is it going to be, well, then does Ceres get to be one as well? Then maybe it's going to be 11. Like, I guess my point is like, it's like people on the one hand, they just want Pluto to remain a planet from I don't know, like they just remember it as one of the planets. But
the good old days.
Yeah, the good old days, right? So I'm fine. Let's do 110 worlds in the solar system. That's fine by me. We've got that many constellations. We've got that many Messier objects. We've got exactly that many Messier objects. I look forward to new.
I think we have more stars in the galaxy than we.
Yeah.
In that.
I look forward to new.
Let me give my a problem with this definition.
Sure.
And I am in no way defending the old definition. Just because one thing is broken doesn't mean that something else can't be broken too. I think that this would be a fine definition if we reintroduced the part about having to be primarily in orbit about a star. That would eliminate basically the moons of the solar system. Mm-hmm. The reason I think this is because the defining characteristics of most moons has to do with their location near a planet. Now, we talked earlier about Io or Europa. These have strong tidal forces because they're close in orbit about a planet. We see a world like Titan has seasons on it. It has seasons on it because it orbits Saturn, which orbits the sun at an angle. It's Titan's relationship to Saturn, or Enceladus's relationship to Saturn, or Io's relationship to Jupiter that defines the sort of day-to-day life or day-to-day processes that take place on these worlds. That's fundamentally different than objects that are directly in orbit about the sun or any other star. And it's okay to have 2 different categories. If we want to have a category for all large objects that meet this definition, then let's just make up a new word for it. But there is a meaningful difference between objects in orbit about a star and objects in orbit about another object in orbit about a star. And I think that
so you're okay with the
definition. To have that
distinction. You're okay with the definition as long as the distinction is that it has to be in orbit around the sun, not in orbit around a planet. So that would knock out a chunk of these objects bring the total number that we have to memorize, the my very excellent mother, and just come up with a new mnemonic.
My definition has problems too, right? Because one area that my definition would leave out is planets that have been ejected from star systems, that now they're primarily in orbit about the center of the Milky Way. But do we want to think of those as planets in the same sense as planets in orbit about stars? Or should we think about those as a different class of object? They don't have seasons on them. They don't.
Yeah.
Go ahead, Paul.
No, I think that's a really good point. I think the point of this definition, to basically make the word planet as broad as possible, is because, and this is the mistake that the 2006 IAU definition made, is that definitions are descriptive. They should reflect how words are actually used in the actual vernacular. So when you look up a dictionary definition of
his internet.
So, how much did we cut out?
You lost
most of it.
Most of whatever it was that you said.
Okay, so I'll try to make it super short.
Just don't move. The key is don't move to overwhelm your internet connection.
Definitions should be descriptive.
Nope. I'll go.
I agree with Paul that definitions should be descriptive, and we have moons aren't planets. That's a common usage description.
No. I mean descriptive as in how people are actually using the words. How many times have I caught myself describing the ice layer on Europa as the planet-wide ice layer on Europa? I don't say the moon-wide ice layer on Europa. I refer to Europa in the vernacular as a planet when I'm describing it.
So you're already predisposed to be able to handle this new definition.
That's the point of this definition, is that if you look in journal articles, Europa is more often referred to as a planet when you're describing the surface, maybe even more than it's referred to as a moon.
I don't know. Morgan, you're a planetary astronomer. Does that mean that you can't study moons?
Yeah, I guess I would say that we ought to come up with a new word that basically fits this definition. And then planets and moons, those are classes of this. Because, scientists aren't the only people who talk about planets. Yep. And just like biology's been able to come up with the idea of having common names and scientific names for species, and chemists have, you buy a drug from your drugstore, it has a chemical name and a common name. There's no reason to think that we can't have a highly granulated scientific definition of what this means while retaining words in their common usage. And I think this definition should, even at this stage, sort of include this idea that we have different categories and not make this sweeping thing and then try to band-aid those on later.
Okay, so Adam Synergy in the chat is saying, let's just call them worlds. What do you think?
That's what I do when I talk about them publicly. I would say Europa is a world.
Done.
And I try to avoid the word planet.
All right. Well, when Alan's turn, I love the fact that he delayed he was busy and he had to reschedule, so he's going to be here next Friday. But now we get a chance to get into this with him. So we will propose from the Weekly Space Hangout crew the term worlds, that there are 110 worlds in the solar system and more coming. That has my vote. Do we have a quorum here? Can we agree? And Paul is, of course, not able to agree, so,
Hey.
All right, well, let's move on. We got a couple more quick little stories. Morgan, there was something else you wanted to talk about? Juno.
Yeah, let's talk about Juno real quick. It got to Jupiter on July 5th last year and has now been there for more than 6 months. But it's got a problem. We talked about this earlier on the show. It's in this long 53-day orbit right now that takes it very close to Jupiter and then very, very far away from Jupiter. And it was supposed to step that orbit down from 53 days to 14 days. And they tried to do this back in November, but they discovered that they had some problems with more than one valve in the engine system of the spacecraft. So they said, hold on, let's stop, let's think about this, let's decide what the best course of action is. Because it might work just fine if you kind of force it, but also the engine could get like stuck open. And then your spacecraft, which is otherwise working just fine, blasts off into space and you lose everything. And so NASA finally came back with a determination this week. And what they said was they're going to keep the orbit they have now. And this has its benefits. Number one, we don't destroy the spacecraft. But also it enables other kinds of science that weren't going to be possible from the closer in orbit. But it also has its drawbacks. The whole point of the closer in orbit was it takes less time, and so you can do more orbits in the same length of your mission. And the whole idea of Juno is to try to map the interior of the clouds of Jupiter by measuring radiation coming out of them from different points around the orbit. Now, Jupiter has these really powerful radiation belts that would basically fry spacecraft. And so we can't just park Juno in a close orbit around Jupiter and say, go to town. We've got to kind of dip in close and then get far away from the radiation for a while. And the good news here is that both the 53-day orbit and the 14-day orbit were supposed to get equally close to Jupiter. So the science is going to be the same quality. It's just going to take a lot longer. What they thought they could accomplish in 20 months, they now think would take an additional 4 years. And those 4 years cost money. They said this could add $100 to $150 million to the Juno price tag if they decide to extend the mission past its planned mission. And that money would have to come from somewhere inside of NASA and probably would come at the expense of another proposed mission or call for another mission later on. So the sort of bottom line is here, we're going to get the science that we wanted to do. We're even going to get what they're calling bonus science, science that wasn't possible from close in, but will be possible from far away. It's just going to take longer and cost more than we originally thought. And that's sort of the danger of spaceflight.
Now, can we blame this at all on gyroscopes?
No, this unfortunately for the Weekly Space Hangout has nothing to do with gyroscopes and everything to do with the firing of the main engine.
Okay. All right. So, I mean, it's too bad that they're not going to be able to get as close to Jupiter as we would like them. I mean, that latest set of pictures that just came out, they were of higher detail than we've ever seen. It was fantastic, and yet it was like these are the closest pictures from Juno that we're ever going to see.
This orbit is at its closest, what we'd call its periaps. Its closest point is exactly the same distance from Jupiter as they were planning to be in this new orbit. It just means for every hour that we spend close to Jupiter, we now have to spend weeks, months away from Jupiter. When before we were supposed to spend a couple hours close to Jupiter, then like 10 days off, then a couple hours on, then 10 days off. Now it's going to be a couple hours on, 2 months off, a couple hours on, 2 months off. We're going to get the same close-in pictures we were before. It's just we're going to have a whole bunch of time spent with the planet really, really, we're talking like millions of kilometers away from the spacecraft, where it's not going to be able to do quite the same things it was planning to do before.
Yeah. All right. So we've got one last thing that I want to just queue up. Did you get a chance to see the SpaceX launch and landing this week, guys?
Very cool.
Yeah. So I'm going to find Elon Musk's Instagram here because it is ridiculous. And I have probably watched this 20 times. So everyone just check this out. So here's what So they had a drone going to watch the SpaceX rocket landing. And we're just going to watch it land. And then we're just going to do it again. Here it comes. We'll just watch it one more time. And we've actually got a article we just put on Universe Today where we had sort of the point of view from a bunch of photographers that watched both the takeoff and the landing. But this one is amazing, right? It's from a drone. So it's sort of panning down and watching the rocket land. So go check out Elon Musk's Instagram page and watch this a bunch more times. I know I could I'll just run this for another hour actually. Anyway, yeah. So it's funny. I mean, we're not gonna sort of go in too deep, but Morgan, you were almost like this is becoming commonplace, right?
Yeah, I mean, this is what, the fifth, sixth, seventh rocket that they've landed. It's, they've done several trips now to deliver cargo to the International Space Station. Even SpaceX, in a sense, I think is kind of reaching for what is going to be the PR talking point of this mission. And it wasn't that they're landing a rocket. They've done that. It's not that they're landing a rocket on land. They've done that. It's not that they're landing a rocket at Cape Canaveral. They've done that. In fact, it had nothing to do with landing a rocket at all. The whole sort of hoopla surrounding this event was that they were launching from Launch Complex 39A,
yeah,
which is where the Apollo missions to the moon launched from. Really nothing at all to do with this mission, its cargo, its goals, etc. I think in some ways we've moved on from the amazement that we can land these things, and now the question is, well, what can we do with them now that we've landed them?
Yeah. And I mean, there's been a little bit more news that's kind of breaking. Maybe we'll get into it next week. That they've pushed the Red Dragon back 2 years, so they were going to be 2018, 2020. I'd like to say that I called it, but and that we're living on Musk time. But I mean, it's obviously
landing on Mars is hard.
Going to Mars is hard, and so expect more delays. And yet at the same time, in the end, we hope Musk will deliver on the promise. All right, well, so we've reached the end of our hour. Why don't we wrap things up here? Morgan Renberg, where do people find out more?
Yeah, you can follow me on Twitter at Morgan Renberg. I generally try to stay out of the planet debate. And of course, you can visit my website, morganrenberg.com.
Dr. Paul Matt Sutter, where do people find out more?
Twitter and Facebook at Paul Matt Sutter and pmsutter.com. That's probably all the time I have before my internet connection.
Oh, that's all you get. You're already turning yellow now. I can see it. Oh, but people should also be aware that that Paul Matt Sutter and I are going to be in Iceland in February 2018, and if you want to join us, you should get on the interwebs. Go to astrotouring.com, and there's still slots available. I suspect less slots than there were last week, just a few. So, yeah, if you want to spend a week with all this bald goodness. And in Iceland,
only bald people allowed.
Only bald people allowed. Then by all means, you should check it out. Astrotouring.com. I think we're gonna have a great time. I'm gonna bring my fancy new camera gear. I'm gonna bring a jacket. You're gonna bring a jacket. Yeah. And I think we're gonna have a great time. So if you're looking for if that's on your bucket list, and hanging out with me and Paul is on your bucket list, then by all means you should join us. All right, well, that's it. I'm going to wrap things up. Once again, I'm Fraser Cain, publisher of Universe Today. We are not going to be doing an astronomy cast after this because apparently there's problems with Pamela's gear. It's finally not my fault. So this is it. Although maybe, can't guarantee it, I might go over onto Instagram and do another hour of just Q&A with folks. So if you haven't already, follow Universe Today on Instagram, Universe Today, and maybe you'll see me pop up there in a little bit, and I'll just hang out and answer questions for an hour. So we've got another episode of The Guide to Space coming out in just a few hours, maybe, talking about TRAPPIST-1. Thanks, everyone, for watching. Thanks to Paul and Morgan for joining me this week. Don't forget to thumbs up this and subscribe if you haven't already. See you later.
Oh, I'm not supposed to thumbs up.
Well, you sure can.
Gonna crash the internet, Paul.
All right. See you later.